This deals with solutions. Preparation and stoichiometry. Reactions in solution phase. So we begin this with the worksheet here, where we're dealing with moles, molarity, and we define the idea of moles. N is defined as molarity times volume of solution in liters. Now, to start this real quickly, the definitions that we need is in molarity. A molar solution, which we identify with a capital M, is defined as moles of solute divided by the volume of solution, not solvent, but solution expressed into liters. And we know that from the definition of moles, sometimes you come out with a mass value and they ask you to convert it to moles and express the solution concentration. Well, moles is the mass solute needed divided by its formula weight. And so that is the mole calculation you need to be aware of. And then you will disperse that into the volume of solution using the methods that we've talked about earlier. Okay, now and this is number one equation. Number two equation, from molarity M equals moles solute over volume in liters of solution. You can calculate moles from this data. N, lowercase n, is a typical symbology for moles. Anyways, solve for moles of solute, and that's molarity M times volume in liters. Now, kind of data that you have to interpret. See if I can get it in here a little bit. Is in problems, buried in problems in terms of solution data. And working problems with solution and solution phase reactions and the such is referred to as volumetric analysis. And so this is a little set of problems that's in Evans text, chapter 4, are solution reactions, and they are asking you how much of one is needed to react with another. And so the purpose of my showing you this at this point is to show you how data shows up in problems. Now, if we read this along with me, what volume of 0.250 molar nitric acid reacts with 44.8 milliliters of 0.15 molar sodium carbonate in the following reaction? So they give you a reaction there. So you have to relate this data to this reaction. And notice how the data in one case is 44 milliliters of 0.15 molar sodium carbonate. That together now, the volume and the concentration terms, they're together like that. It's called solution data. And you use those together to convert to moles. So in this particular case, molarity times volume, you express that in liters by moving your decimal 3 places to the left. When you multiply those together, you'll have the moles of sodium carbonate, and that would be related here to this part of the equation. And then you have 0.250 nitric acid up here, and if you take molarity times an unknown volume, that would be related here, but molarity times volume here equals 2, well actually it'll be 2 times this one, because you swap your coefficients. We'll do this later in more detail. And so these two would be equal if you double the one on the right. And then solve for your volume in here. It's asking you, and then you would have the volume that would neutralize this, because it's a 2-to-1 reaction ratio. I'll try to spend enough time on these reaction ratios to give you a lot of experience. And so, but the main thing right now in working solution phase problems is that you recognize terms like this: 49.8 milliliters of 0.1 calcium hydroxide. And here's, let's see, now this one's in mass, volume, molarities. Look down here. Some of them, they come in various forms. Let's see. Yeah. Here we go. This one, you see here is 51.7 milliliters of 0.145. So the combination of these, you should be very quickly relating to moles. And why? Because you want to relate the moles to the equation, solve that mole ratio by ratio proportion, and get your unknown. And if they want it back in some other terms, then you convert it back. But this is how solution data comes to you in a lot of these types of problems. Okay, so now we have the two ideas in terms of working with solutions and solution concentrations right here. And this is what we want to work with in our problem set. So on the side, maybe on a scratch paper, write down molarity, M equals moles over volume, moles over volume. Moles of solute over volume of solution. And molarity, and moles is equal to molarity times volume. So kind of on the side, because all of these questions revolve around these combinations of terms. Okay, I want to give you a clear perspective on what the difference is between moles and molarity. Several times I mentioned moles is a mass number, molarity is a concentration number. And it's kind of like density, mole divided by volume in liters. Okay, so first problem that we want to look at, it says how many moles of HCl, that's your solute, are there in 35 milliliters of 0.55 molar HCl solution. So how many moles of HCl in 35 milliliters of 0.55 molar HCl aqueous solution. Right there. That. Well, from the equations given, we know that moles, and that's moles of solute, is equal to given molarity times volume in liters. And so I can't say this enough. I know it sounds redundant and it gets kind of aggravating to many of you, but eventually it will come across to all of you that this is the shortest line between certain kinds of data and the equation. And that's what the purpose of this relationship is. So moles HCl absolute, because we're talking about the moles of compound, is equal to, we're talking about a 0.55 molar solution, and we have 35 mils. Well, you want to move the decimal 3 places to the left to give you liters. Okay, so 0.035 liters. Okay, now molarity here is moles per liter. We've already talked about that. 0.55 moles per liter times the 0.035 liters. And so when liters cancel out, we're left in moles that we can relate to an equation or whatever reaction we're wanting to deal with. Okay, so this would give us a molarity, from a molarity volume into moles, of 0.01925 moles of HCl solute dissolved in that solvent solution, or dissolved in the solution. Now, the data that is given, it just looks on either side 2 significant figures. So from left to right, 0.019 looks like 19 mole of HCl. Let this go. Okay. Like that. The second problem, if I'll put it up here and you can read it with me. If 0.15 moles of sodium chloride are in 125 milliliters of aqueous solution, what is its molarity? So you're going to use the definition of molarity and apply that to this data. So given solute is equal to 0.15 mole sodium chloride, and it's dissolved in that solution, and the volume of solution is equal to 125 milliliters. So the molarity, based on the definition of molarity, moles per liter, as I've been indicating, this case would be moles of sodium chloride, volume of solution in liters. Well, of course, we'd need to take, if there's anything but moles, if it had been grams, like you said, it would have to be converted to moles. Well, we're given moles, so we don't have to make a conversion right there. And volume of solution, though, has to be converted to liters. So move the decimal 3 places to the left, and it gives you 0.125 liters, and that goes into the equation. And so this will give us, out of the calculation, 1.2 molar in sodium chloride. And so this is a common phraseology that's used to describe solutions in terms of the data we've got. It's 1.2 molar in, or is active, 1.2 molar active in that reagent, sodium chloride. So 1.2 molar in sodium chloride is the number 2. Let me see if I got enough room, but I'll do number 3 on this page too. Okay, number 3 is asking us here, what volume of 0.22 molar sodium hydroxide solution will contain 2.5 moles of sodium hydroxide base? Okay, so we're given 2.5 moles of sodium hydroxide in a 0.22 molar solution. What is the volume of the solution? So we're looking for a volume number, and we're given moles and solution concentration. So from the same definitions, moles equal molarity times volume, or from the definition of molarity is moles over liters, we can solve for volume in either one of the cases. So moles equals molarity times volume in liters, and so we want the volume in liters is what we'll come out with, and that's moles solute divided by molarity of solution, like that. So in this case, we look through the moles given is 2.5 moles sodium hydroxide over 0.22 molar solution. Now, just to put this in perspective, put the M into moles per liter, and it's moles over liters, and then when you invert and multiply the denominator term in that form, you wind up with units liters when everything's said and done. Okay, so we're showing 11.36, and 2 sig figs would probably be sufficient. So this is about 11 liters of solution in significant figures.
So this is the mole among.
Okay, here in the proper terms, we have moles over molarity. You see what I'm saying? Mm-hmm. That's what's given here. Moles, molarity. Well, molarity, as we know, is moles over volume in liters. And so to simplify by math, it's just a ratio. This will give you moles over 1 times volume in liters over moles. And so moles cancel out, and we're left with volume in liters, like that. Everybody okay? And this one, what is the molarity of a solution prepared by dissolving 23.45 grams of sodium bromide salt in water to give a total of 150 milliliters of aqueous solution? And I gave you the formula weight as 81 grams per mole. So what's been said is that we need to convert to our mass number into moles and then put it into the moles per liter equation. Okay, so this is number 4 in our problem set on solutions. You're given 23.45 grams of sodium bromide in 150 milliliters solution. And you're also given the formula weight of sodium bromide to equal 81 grams per mole. So when you have a problem that is grams or mass number in grams or anything else, you still have to convert it to moles divided by liters. And this is the most common presentation in grams in most exams. So we know the molarity is what we're looking for, is moles sodium bromide in volume of solution in liters. Now, moles of sodium bromide, grams is converted into moles by dividing by formula weight. So we take the 23.45 grams divided by 81 grams per mole, and we kind of bracket that as a numerator, and divided by the volume needs to be in liters. Let me correction, sodium bromide is 104 grams per mole. Substituted into the definition moles, grams mass over formula weight, and that term, or that quantity, divided by 0.150 liters will give us the molarity. So we have 1.50 mole per liter, or molar, in sodium bromide aqueous solution. Guess my correction. What is the molarity of an aqueous solution if 0.2074 grams of potassium hydrogen phthalate dissolved into enough water to give 100 milliliters of aqueous solution? And I give you the formula weight, 204.32, some 204.22, just use that. Now this is what you will have to do Thursday. Your group will have to make a solution from the KHPH salt, and you'll also have to make solutions from the HCl and sodium hydroxide. So this is kind of a practical heads up for the lab we're going to do on Thursday. Okay. So we're given an aqueous solution that it contains Okay, so we're given an aqueous solution containing 0.2074 grams of KHPH and is diluted to 100 mils, and solution volume is equal to 100 milliliters total. Okay, and the formula weight of KHPH, potassium hydrogen phthalate, is 204.32 grams per mole as given in the problem. So molarity of that solution is the unknown. So we know that molarity of the KHPH solution is equal to moles of KHPH divided by volume in liters. So again, in calculating the moles, we divided by formula weight, and so here is this time the formula weight is going to be 204.32 grams per mole divided into the 2074 grams. And that's going to be divided by 100 mils of water in liters would be 0.100 liters. And so I'll bracket this off as the numerator so it kind of sticks out a little better. So, setting it up, this is your conversion to moles divided by volume, and it came out 0.0010 mole per 0.100 liters, and that's 0.01 molar in KHPH. Okay, this next set, the next couple of sets in here, or next three sets, are the lab procedures that we dealt with and talked about in class yesterday. So we want to do a set where you have problems in determining how much from a solid stock, how much volume you need from a strong acid or concentrate, and then some dilution formula problems. So this will give you a nice set of model calculations that will be like what you will see come exam day. Solutions prepared from solid stock. First, let's just get the formula down. This refers to grams of solute needed is equal to molarity times volume in liters times formula weight of the solute divided by a purity factor, which scales it up and down based on the purity of the manufactured sample. Okay. So a practical question would be like number one, how many grams, well, I'll put it up here so we can read it together. How many grams of reagent grade KClO3 would be needed to prepare 250 milliliters of a 2.25 molar aqueous solution? And then I'll give you the formula weight, and then we'll assume the stock purity is 100%. Okay? So you are given, we'll put the question down first. Okay. How many grams of KClO3 solid would be needed to give 250 milliliters and 2.5 molar solution of the solute given. So just simply using this expression here, we see grams of KClO3 needed is based on molarity, volume. We'll have to convert that to liters. We're given the formula weight in the problem, I believe. 122.56. And the purity factor is 1. So molarity is 2.5 molar, is what we need. Volume that we will need is 250 mils, and that has to be in liters. And formula weight is given 122.56 grams per mole. And the purity factor is 1.00. Like that. And so the outcome of this will be in grams because moles will drop out against the molarity. Moles over liters, liters will drop out against the molarity also. I got 76.6 grams of KClO3 needed. And in the process, transfer 76.6 grams, or very close to that, grams KClO3 solid into mixing container. Add solvent, water, amount less than total volume needed. Dissolve, transfer to volumetric, and dilute up to but not to exceed 250 milliliters total volume.
I think it's supposed to be, I think.
Anybody still need some time? Raise your hand if you need more time. I'll give it to you. Keep going. Okay, we continue. Problem 2. A solution of sodium acetate is prepared by mixing 135 grams of the salt into water to make a 225 milliliters aqueous solution. The assay purity, wait a minute, I already gave it. All right, look. A solution of sodium acetate is prepared by mixing 135 grams of the salt solution into water, and you wind up with 225 milliliters of aqueous solution. Now the thing is, it's only 96.2% pure. That's what you got off the assay bottle when you got it. Okay? So when you add 135 grams of the manufactured stock, you're not adding 135 grams of reagent. You're adding less than that. Now, if you put 135 grams of the salt in there, it's of the reagent. Again, it'll have less than 135 grams of salt. See, what you're putting in is only 96% or 96.2% of the 135 is pure sodium acetate. The rest of it is garbage. And so the problem is asking you to tell exactly how much mass of true sodium acetate is in that solution. So we're given 135 grams of sodium acetate that is 96.2% by weight active from the manufacturer. how many grams of salt is mixed into the solution, and what's its polarity? I forgot to put that in there. Okay. If we calculate the molarity based on 135 grams of the sodium acetate added, we'd be wrong in its concentration terms. The mass of pure salt is 96% of what's added. So the mass of pure NaOAC, that's abbreviation for sodium acetate, you'll see it again in the future, is equal to 96.2% of the 135 grams of MFG reagent. Okay. So that's going to be equal to 0.962 times 135 grams. Okay, I get 129.87 grams of NaOH 100% if it hadn't have been pure sample. So that's how much real chemical is in the solution. Does everybody have an understanding of what how this purity factor is used now? It's saying that all of what you get in there is not true 100% pure compound that you need. A certain percentage is impurities. Now, once we get this number, then we can get the molarity based on the definition is the mass of sodium acetate divided by the formula weight and then divided by the total volume in liters. So we have 129.87 grams of sodium acetate, and it is 82.03 grams per mole, and that's divided by 225 in liters, or 225 milliliters converted to liters. So I'm showing a 7.04 molar stock in sodium acetate. Yeah, but we got, let's see. No, you don't use that one. You'd have to use 1, 2, 3, 4, 5 sig figs, and throw in another couple of zeros in there if you won't worry about it. Because you have to round it to the data if you're going to do an academic problem. But you again round it if you're using an experiment with this. You round it to the least accurate. Okay, this quantity that's put into the solution, is that all? How much is pure stuff? 96.2%. So when you take 96.2%, that's most of it, almost 100. So you get a number down here, 129.87. That's quite a bit. And the difference between 135 and 129.87 is junk. Okay. Here, what volume of lithium hydroxide aqueous solution would contain 63.2 grams of lithium hydroxide 100%. Okay, so we need to find out how many what volume we have of lithium hydroxide solution that is 1.55 molar in the reagent, and we contain 63.2 grams of lithium hydroxide. Well, from moles equals molarity times volume, of course expressed in liters. We can solve for volume in liters and get moles over molarity. So that would be the moles of lithium hydroxide divided by the molarity of the system. So the moles of lithium hydroxide is 63.2 divided by formula weight. So I have 63.2 grams in solution divided by 23.95 grams per mole. So that takes care of my mole. Divided by the molarity it's given is 1.55 molar. Right there. And so, now remember, molarity is moles over liters. So if I take out moles and liters, well, we're trying to solve for that. And grams fall out. I'm left only with liters in the final answer. And you convert it to whatever you want, milliliters, whatever. And 1.702 liters. And if you needed to, 1,702 milliliters. And if you're using 3 sig figs, then that would be 170 like that in milliliters. And just drop the 2 on the end, and you'd have 3 sig figs. Okay, let's take about a 15-minute break. Come on back. When I finish, I've got 2 more sets. We'll call it a day after that. I'll start gas walls. Talk real fast. quickly, and I got these equations, exclusion equations. Is the grill still open? Anybody know? About this time it's 12. Well, it ought to be open at 12, isn't it? That's not a chemistry question, so you can answer it. Just kidding. Is the grill still open right now? I would think it would be. I'm going to go get something to eat. You don't know? Well, I'll forgive you this time. You doing all right now? You coming on? Did you get my note last night? Did you get my note last night? Okay, so we'll try. I don't know if it'll be immediately, but we'll try to get the lab names up somehow. The trouble is, they tear them down so fast when we put them up, put up the equipment and stuff. I'm thinking it, I could probably grab it pretty quick. I think with me, I'll do one right here. I've been wanting to do it over anyway, and use that propane torch I've got, and heat it stronger. So we may in the next few days or next week or sometime. Get a minute, after class or something, we'll run it. Okay, fill it in for you.
Do you have a test?
Yes, it will.
When you miss, that D lines up in the bubble brush, okay? Like that C lines up this one. So you should have chosen C choice and that one, and B choice and that one. And you see how they look like? Okay. And the other question, 4 lines first and look at the proof. If you haven't looked at it, when you can't find it, let me know. If you still have questions after that, then I'll be glad to.
Okay, this section is solution prep from manufactured stock, and that's liquid form. And so the primary equation for this, is right here, is you're looking for a volume, and the equation is almost identical to the solid stock problem, except we have specific gravity or density if the solute is water. So in working with these, the question is how much or how many milliliters or whatever volume is appropriate, how many milliliters of manufactured stock will be needed to prepare needed solution. So that's the essence of this section. So you use the expression volume in milliliters needed is, when I write it out, you'll see it's almost identical to the grams needed. That's molarity times volume in liters times formula weight of the solute. It's the primary solute of the solution, and it's also divided by the purity factor, which is the concentration of the manufactured stock. But to get it to milliliters, you have to also include or divide by specific gravity. And note, specific gravity equals density in grams per milliliter if solvent is water. And for the most part, concentrated acid solutions, when they arrive, will be in water stock and water solvents, water solution, aqueous solution. So, first question here in this set. So, one of the emphases in my presentation of this topic is safety. And so the first question is really not a calculation, but is a review of the methods that I'm trying to impress upon you that are important in making solutions from very corrosive materials, like in this case strong acids. So what is the accepted safe practice of mixing a concentrated and manufactured strong acid into water to prepare an aqueous solution of that acid? Okay, well, in practice, if you're given strong acid concentrate, and you want to follow a certain prescription of mixing this together. After determining the quantity in milliliters that you need, you first you add a quantity of solvent, water, and an amount than total volume needed, of solution needed. Add a quantity of solvent water in an amount less than 2 mixing container. And then B, cautiously add volume of stock concentrate into solvent and stir to homogeneous. Okay. The purpose of doing it in this order is to prevent the rapid ionization of the strong acid. And by pouring the acid into water, the acid will ionize much, much slower and not generate as much heat, much safer. Finally, transfer mix into volumetric and dilute up to needed volume. So the emphasis here is, of course, on safety, and you want to wear appropriate protective clothing, goggles, aprons, rubber aprons, rubber gloves, whatever. Small drops get on your jeans or whatever, they'll eat a hole in it in a heartbeat. So you want to be very, very careful with strong reagents like this. HCl becomes about 37%, nitric acid about 60+%, sulfuric acid 98%, and some of those are very, very dangerous. And they're fuming also. Fuming strong acids are not to be sniffed, and typically they're kept and mixed under fume hoods. So just be sure you read the MSD if you're going to use this stuff, and be aware of the hazards and handling procedures. So here, what volume of manufactured stock HCl, and I'll give you 37%, would be needed to prepare 100 milliliters of 3 molar aqueous solution, and the specific gravity is 1.14 and formula weight 36 grams per mole. Okay, so we want to prep 100 milliliters of 3 molar HCl solution in water, aqueous solution, and the HCl concentrate 37% active, and HCl, its specific gravity is 1.14, which gives you a density equal to 1.14 grams per milliliter because the solvent's water. Use the formula weight of 36 grams per mole. Chloride's 35, hydrogen 1, 36 grams per mole. And the volume in milliliters needed course, is molarity times volume times formula weight divided by purity factor. And again, specific gravity has to be included in the expression. And so the molarity that we need, 3 molar. The volume needed is 100 milliliters. In liters, that's 0.100 liters. Formula weight, 36 grams per mole. Purity factor is 0.37. So that's the 37% converted to a decimal fraction right here. And then your specific gravity, which is the same as your density number, is 1.14. And I'm going to go ahead and put in grams per milliliter so I can show you the evolution of the unit set. This comes out of this thing. So if we just look for a second at the sidebar, molarity is moles. Let me bring that down here. Molarity is moles per liter, and times liters times grams per mole, and that's going to be divided by, the purity factor doesn't have any units, it's a percentage thing, and divided by grams per milliliter. And so if we go through here and cancel out the units, moles will cancel, liters will cancel, grams will cancel, invert and multiply, and so the units wind up in milliliters. When we multiply this set, solution set, okay, right here I want to change that to 1,000, and of course that would change to 1 liter, and it will come out in milliliters as we've shown earlier. So while it seems like a lot, we're making a kind of a lab stock. When you go into making lab stocks, you'll probably want to make them in the 3, 4, 5, 7, 8, 9, 10, and probably not really actually higher than 5. And it's just arbitrary choice, but this is going to serve in making many dilutions of the sample, whatever. Now, one thing you need to note is this is honestly quite a bit of strong acid, 256 mils. And so if you think of it, 256 mils, you know what a 250 beaker is. So you start pouring water on top of that. That's what I'm talking about. That quantity of acid is very dangerous, and if you mix it the wrong way. Many people use the expression A&W root beer, acid to water, A&W, acid into water, and then you dilute to needed concentrations. This third one is if 50 milliliters of concentrated nitric acid is used to prepare 2 liters of 5 molar aqueous solution, what is the molarity of the manufactured stock? Specific gravity, 68% nitric, is 1.42 grams per mil in density terms. So we're given 50 milliliters of HNO3, and it looks like 68% concentrate, and the volume of solution is 2.0 liters, and concentration is 5.0 molar aqueous. Brackets like this, they'll be used many times from here through the end of this course. Many, many times. This bracket is an understood symbology that means moles per liter or molar concentration. Is whatever that bracket it is, that the acid or whatever reagent you have in that bracket, and they give you a number, is the concentration term, and in molar concentration term to be specific. So if you, I don't remember putting that up at all up to now, but yeah, the bracket means molar concentration, long and short of it. Okay. Now, in this one, you have a volume of concentrate in milliliters is equal to molarity times volume in liters times formula weight divided by the purity factor, and let's see, and specific gravity. So you got everything in here, and it wants to know what the concentration of the, it's got a 68%. What's the molarity of the manufactured stock? I don't think you need to use that at all. There are probably a couple of ways to do it. You're also given a 68% nitric acid solution. And what that means, you have 68 grams of HNO3 per 100 grams of solution. Now, if we want to get that to moles per liter, what do we have to have? And of course, that would give us the molarity of the solution. So you have to take, you know how to take grams and convert it to moles by the formula weight. But this is a solution. And to get that to liters and milliliters and volume, how do you do that? Well, you use the specific gravity that they give you in this. The specific gravity is 1.42 grams per milliliter. And so this is a gram weight, and you can use the specific gravity term, 1.42, into that number right there, and that'll tell you how many milliliters your solution is. If it starts at 100, this is just a standard. So to get this to moles per liter, we'll have 68 divided by the formula weight. There we go. So I got 63 grams per mole divided into the 68, which would convert that portion to moles. But I need to get this into liters. So I have 100 grams, and if I multiply that by 1.42 grams per milliliter, right there, then the grams would cancel out. Now I want to divide by that. I'm sorry. I want to get the denominator into a volume. My bad. Okay, so that would be divided by 1.42 grams per milliliter in the denominator here. And so, okay, this will compute here to give us 1.079 moles, and then when we divide by the specific gravity, or divide that into 100, we invert the units and multiply, we get milliliters. Of course, that has to be in liters, so we move the decimal 3 places to the left, and we have 1.079 mole divided by 0.07042 liters. that's 15.32 molar in HNO3 for a 37% solution. 15.32 molar, quite a strong solution. Now you can take that data and go to the dilution equation, and it'll work just fine also. Okay, solutions prepared from lab stock concentrate. So what we're talking about here is you will have prepared pre-lab some stock concentrate that has a high concentration of whatever you're going to be using many times over. And this keeps you from having to use a concentrate all the time in mixing your samples. Well, in the idea of solutions, we start out with, say, a manufactured stock. Okay, and say that has, okay, you've got, say, 945 grams of nitric acid. Okay, now I'm just taking this as a hypothetical. And you double the volume, and it's the same question I asked the other day. How much weight of HNO3 do you have now? In here. Remember that question? When you, regardless how you dilute it, you still have the same mass. You still have 945 grams. Well, if I convert that to moles, I divide both of them by 63, or 63 into 945, and that's 15 moles in this one, and still 15 moles in number 2 over here. So regardless of how much solvent I put on the solute, it still has the same mass of solute in both beakers, but the concentration has changed. Now, since moles of solute equals molarity times volume, and you can leave it in milliliters, primarily in liters, that's all right. Moles equals molarity times volume, then I can take molarity times volume of the diluted sample and set it equal to the molarity times volume of the concentrate. And we'll have what we call the dilution equation. That'd be molarity times volume of the concentrate will be equal to molarity times volume of the diluted solution. This is what you wish to make, and this is your lab stock concentrate. And so in preparing solutions, the question you want to ask is what volume of stock, let's try lab stock concentrate, will be needed to prepare a needed solution. So you are going to extract a certain quantity of the concentrate, transfer to the mixing container, and add water up to but not to exceed the total volume. And of course you can transfer it into a volumetric, because that's not going to make a mess like the others do. So this is more of a convenience type issue, but it's widely used in changing the concentration or making different concentrations or diluting concentrated systems. And so these are still moles equal moles, and so mass combinations. All right. Knock out a couple of problems here. Okay, the dilution equation problems. We've got one here. It says, what volume of water must be added to the 30 milliliters of 5 molar calcium chloride to dilute it to a 1 molar calcium chloride solution? So you've got molarity. Let's get the given down first. Let's see. Your given concentrate is 30 milliliters of a 5.0 molar calcium chloride aqueous solution. What volume of solvent will dilute it to a 1 molar calcium chloride aqueous solution? So this is either way. So you have concentrate over here and your diluted sample here. Now, typically, I've been teaching you, well, you figure out what volume and concentration you need and then solve for the volume of concentrate. Well, here it's kind of backwards. We just want to figure out what volume will dilute this thing down to 1 molar. So molarity times volume of the concentrate is equal to molarity times volume of the diluted sample. Now, I recommend molarity, make a table, data table, molarity concentrate, volume of the concentrate, molarity of the diluted, volume of the diluted samples. And fill that in and substitute, solve for the unknown based on your givens. Well, we're given 30 milliliters of 5 molar acid solution, salt solution. The target molarity is 1 molar. And so the question is, what is the volume of solvent we need to pour on top of 30 milliliters of 5 molar to get the dilution to 1 molar? So molarity times volumes of the concentrate, so that'd be 5 molar times 30 milliliters is equal to 1 molar times whatever that volume of diluted. I can leave that in there as a variable. Volume of the diluted. And the volume of the diluted is, of course, 5 molar times 30 milliliters of concentrate. About 1 molar, molarities drop out, and you have 150 milliliters. So of solvent will dilute the 30 milliliters of 5 molar to final concentration 1 molar. Now here's one thing you may not be seeing in there. What's your final volume? This equation tells you how much of the solvent you pour onto the existing solution. Well, the existing solution is already at 30 milliliters. So 150 milliliters plus 30 milliliters, after you pour it on top, gives you 180 milliliters final solution volume. So that's kind of a hidden issue in this kind of problem. So your final volume is not, and that's why I give this problem, your final volume is not that you throw 150 mils, it's 150 on top of the 30. So that's a check mark you need to certainly pay attention to, in that we are diluting something with a solvent. Now, if it's a matter of extracting a concentration, an amount of concentrate, to produce a final volume, then yeah, that'll be the final volume. Let me see if this next one does that. Not exactly. Yeah. Okay. Okay, this last one, if 60 milliliters of water is added into 80 milliliters of 2.5 molar HCl, what's the final concentration of the solution? So this takes a little bit of a twist. You can still use the dilution equation, but let's look at it from a different perspective. You're given 80 milliliters of 2.50 molar HCl aqueous solution. Add 60 milliliters of solvent. What's the final concentration after adding the solvent? Well, the first question you need to check mark is, will you be more concentrated or less concentrated? You'd be way less concentrated, right? Okay, so you want to look at, when you finish this, the concentration number that you get should be less than the 2.5 molar. So it's some common sense into problems like this. Okay? Next is you apply the definition of molarity. That's what it's asking you to do. So you can use the molarity times volume of the concentrate is equal to molarity times volume of the diluted sample. And the unknown part is the molarity of the diluted sample after you pour all the solvent in on top of it. Well, the molarity of the concentrate is 2.50 molar, and you have 80 milliliters of it. And that's equal to the molarity we're looking for, and the volume of the diluted sample. Well, what's the volume of the diluted sample? It's the combination of these two. 140 milliliters is your final volume, because you're pouring 60 milliliters on top of it. So you got to watch for these kind of things, and that's why I asked, will you be more dilute or will it be more concentrated? So when you dilute something, you're adding more to the final solution, and that's what I want you to get in the mental frame of seeing that you're adding to the total volume. So this should be 140 milliliters listed in here. And then solve for your diluted sample. Molarity diluted is equal to 2.50 molar times 80 milliliters divided by 140 milliliters, and 80 over 140 is a fraction anyway of the 250 milliliters will drop out, and the final concentration .43. So that is the final concentration. So these last two problems have a twist in them that's hidden, in that you have to interpret in terms of adding to the final solutions. And that brings me to reactions in solution. We have applied all the basic concepts in preparing solutions. Okay, so summarize, for solution preps from solid stock, solid manufactured stock, of course, molarity times volume in liters times formula weight over purity factor. From liquid manufactured stock is molarity needed times volume needed times formula weight of the solute divided by purity factor and specific gravity. And this will come out in milliliters. This one will come out in grams. And then you have from laboratory stock concentrate, you calculating how much you need to pull out of the concentrate and dilute up to, but not to exceed the final volume needed. So this is molarity times volume of the concentrate is equal to molarity times volume of the diluted. And this is your needed, and this is your stock concentrate. Now, many people will post this in their notebooks, or take the entire page, the page one from this that hopefully you saw the procedures, and put it in their notebook somewhere where they can review it. Because of all the things that you do in chemistry, if you stay in here, solutions are going to be a dominant part of your life in chemistry. And so you need a place to go real quick to review these methods and take care of business as needed. So what we want to do is look at solution phase reactions, or reactions in solution. Typically acid, base, or salt type reactions. So we're looking at acid plus base to give a salt plus driving force, which is a precipitant, a gas decomp, or a weak acid or base. And then you have and all of this is metathesis, as a matter of fact. Now you have combinations in solution, and other things, but the ones that are really red line important to you are those that are metathesis reactions. Then you have a salt plus salt goes to a soluble salt plus an insoluble salt. This, of course, would be the driving force of the reactions, and this is a soluble salt. And these two are, on the reactant side, are soluble salts if they are metal and nonmetal combinations. Now, if one of those on the reactant side is weak electrolyte, like a weak acid or something reacting, and there are plenty of acid-salt reactions that work, you'd have to maintain the molecular form on the reactant side, but we'll get to that later in here. So the primary form of these two reactions is metathesis. AX plus BY goes to AY plus BX, and stoichiometry comes out of that relationship after it's balanced and so forth. Okay, so we want to try to work some problems. Now, what kind of problems have we worked in, topics have we covered in reaction problems, stoichiometry? Well, we've looked at mole reactions in which we calculate given moles, and we have to calculate a yield in moles. We are given mass in grams of one reagent. I should have written it like that instead of as yields. Product mass in grams. Well, you can work it in grams if you want to, but it's a lot more difficult. You convert the grams to moles and then convert it back to grams at the end of the problem and this kind of thing. Now, a third thing we've looked at is what we call a limiting reagent. This, of course, is when one of the components is in large excess of what's needed, and the other component is in will be used up first, and you'll have one of the components left over when it's finished. The component that goes away first is, again, the limiting reagent. Okay, and so for problems associated with limiting reagents, you have to determine what the limiting reagent is and make the yield calculations based on that limiting reagent. And you may remember that. And then, of course, you still have the percent yields, which is the lab yield versus the theoretical yield kind of thing. Who's in excess and who is, in the limiting reagents, who's in excess and who's gone first. And we'll go ahead and put the percent yield, which is the lab yield over theoretical yield times 100%. And the whole issue that I preach constantly is convert data to moles and convert solve problem and then convert to needed dimensions. So, in all of what we've done so far, this has been the underlying objective and theme of me teaching you how to deal with this. Why? Because moles is the easiest way to go. Moles is the direct ratios in the balanced equation. And you can set up a very simple proportionality equation and solve for the unknowns very, very quickly. Okay. Here's your first problem, reaction solutions. Say you're given 25 milliliters of 0.65 molar HCl is mixed with 35 milliliters of 0.55 molar sodium hydroxide. Well, which of the reagents will be in excess after mixing it? And what will be the relative pH? Now, when I say relative pH, acidic, neutral, or basic, that's all. Is it above 7? If it's pH greater than 7, your conclusion is this is a basic solution. If pH is equal to 7, then you're a neutral solution. If you have a pH less than 7, of course you have an acidic solution. So a basic solution would result from an excess of compounds delivering OHs in the solution, or OH ions. A acidic solution would be an excess of hydronium ions or hydrogen ions. And a neutral solution, the molar concentration of hydronium ions is equal to the molar concentration of hydroxide ions. That's why it's neutral. You only have salt affecting the solution. First thing you need to do when you have a reaction in solution is determine what the reaction is and balance that reaction. Well, looking at this, we have 25 milliliters of an HCl going here, and then we have 35 milliliters of NaOH going here. So recognizing the HCl plus NaOH as the reactants, then I'll come down here and go NaOH, and let me put acid first. HCl, and a lot of them will write aqueous. Plus NaOH, aqueous. And this is a double replacement now, metathesis. Just to review, AX plus BY goes to what? Okay? You take the outside ones, remember how I told you to do that, and then the inside ones, put them together. And I like to suggest you put the driving force, in this case water, and most of the problems will be water, on the end of the reaction. So NaCl aqueous plus H2O, and that's your driving force. So we've gotten the equation, and it is balanced. This is one of the simpler acid-base reactions. All right, now this is a format that I use. You can use whatever you want, but I find this helps me keep up with the bookkeeping, so to speak, in working through one of these kinds of problems. Okay? So again, I put a little bar out here, and so essentially what we have is 25 milliliters, and then I put the solution concentration now of 0.65 molar HCl plus 30 milliliters of ml 0.55 molar NaOH. Now it's spread out across the entire page. You don't think about yields at this point, because from the equation, when you convert this to moles, you'll see exactly what your yield is going to be, and you will note the excess from that. So the rule is, 1, convert to moles, and then convert back something else if you need it later. To solve the problem in moles. So looking at the data that's given here in that problem, what do we call it? Solution data, right? And when we got solution data, and if I want moles, I have to go molarity times volume, where the volume is expressed in liters. Well, I can do that ahead here. So molarity times volume, so I'll go volume times molarity, whatever. This has got to be converted to liters. 0.025 liters, but I don't put the units down there yet. I put 0.025 times 0.65 mole HCl. See what I did? Because I know the product of those two, if done this way, it's going to be moles anyway. So I wanted to get it in moles, so I just put the two numbers together, the product, and put mole over here, because that's what the unit is. And then the same thing here, you have 0.03 times 0.55 mole of NaOH. And so from there I continue with just processing the problem. So first thing I do is multiply 0.025 times 65, 0.65. And so I have 0.0163 mole of HCl. And then I multiply the next two numbers together, 0.03 times 0.55 equals 0.0165 mole of NaOH. Now, from the equation that we wrote back here, what is the reactive ratio? Let me do this a different way. I'm going to rewrite the equation. From this, we have HCl plus NaOH, and that goes to NaCl plus H2O, the driving force. Well, from what we've just calculated, if we attach these numbers to this reactant side, then HCl is 0.0163 mole. Here, and I've got a little bar right there to just separate or partition the two. And 0.0165 mole of the NaOH, right? So we did that here, and I'm just putting it in a perspective, because the purpose of doing this right here, getting it into moles, is so you can relate it to the equation. And so that's the most important part, is that you put the chemistry with the numbers. Now, what does this tell you? How many moles in the standard equation? 1 mole against 1 mole. So 1 mole will completely neutralize. So in this equation, it's given the reactive ratio is 1:1. So if I have so many moles of acid, the same amount of moles of base will react with it and neutralize. If there's anything else there, is excess. So I look at these two, and I see, well, I've got a 163 and a 165, whatever. This one's in the least amount, and it's a limiting reagent. I could divide by 1, but both of them are divided by 1. Okay, you remember how we did that? Divide by the related coefficient, and the smaller of the two gives you the limiting reagent. But we divide both of them by 1, here we have the moles. Well, the smaller value is limiting reagent right here. So now I come down in here, and what is this telling you? When this reaction finishes, what have I got in the beaker? All of the acid is gone, because this is the one in the smaller amount. And the amount of acid converted will also be the amount of salt. So the salt generated over here is equal to the limiting reagent consumed. Because for every bit of HCl consumed, you're going to make a sodium chloride every time. But if you have more than the limiting reagent, it ain't going to make anything. It'll stay there by itself and sit there and mope because it didn't have anybody to react with. So the smaller value is limiting reagent. So this next consideration right here is what's left. That is excess NaOH that remains and sodium chloride in solution. Excess. This reacts 1:1. So that excess NaOH is just going to be the difference in those two. For every 0.0163 mole of HCl, I'm going to use up 0.0163 used. So I'll subtract that. Mole of sodium hydroxide used. Well, I have .0165. That's more than I'm going to need. What does that mean? That means nothing's going to happen to that excess. It's just going to lay there because the salt's not going to react with it. Okay, so when I come down here and I make that whose excess, it is 0.015165, sorry, minus 0.0163 mole NaOH in excess. And you also have in that mix a salt equal to the amount of HCl consumed plus mole plus moles of limiting reagent. It could be either one of it. You'll still get the same issue, the same concentration of salt. If we turn this around and made this a limiting reagent, the NaOH turned out to be a limiting reagent, it still produced the same number over here, but you'd have excess in HCl. So the moles of salt equals the moles of the limiting reagent used. Okay, so that's what's in the beaker. So here's your after mixing concentrations, or you have quantities anyway. You have 0.0002 in exit mole NaOH plus the amount of moles used, 0.0163 mole salt, because it's the same as a limiting reagent. Always, same as a limiting reagent. The final step in these kind of problems is to put it back in concentration terms, moles per liter. What you've done here now is you've mixed 25 milliliters with 30 milliliters. So it's a 25 plus 30 mix, which is a 55 milliliters in the final solution. So you take that against the moles. What's the definition of molarity? Moles over liters. So this is your liters. You can convert 0.55 milliliters to liters, 0.055. And divide those into each one of the remaining excesses. Or if you want the molarity of the salt, also divide it by 0.055, and you get both of them. So the concentration of NaOH in moles per liter in excess is the 0.0002 mole remaining in excess over 0.055 liters, which is the 30 and the 25 mixed together. And then if you want the sodium chloride produced, or the new molarity of the sodium chloride, let's just do it that way, salts. I don't know what you'd call it other than that. Well, that is equal to the limiting reagent used, which was the HCl, and that's 0.0163 mole of salt produced from the 0.0163 mole of acid consumed. And that's also divided by 0.055 liters. They're both in the same bucket.
0.5 was right at
0.0036 molar AOH. Let me get 0.0163 divided by 0.0 equals 0.264 molar NaCl. So these are your two final concentrations in the solution after the reaction is. Let's make a little notation. I use 30 milliliters NaOH and mix instead of 35, and so it mess up the whole delivery thing. Let's say we have 28 milliliters of 0.11 molar sodium chloride is mixed with 22 milliliters of 0.18 molar lead nitrate. Determine mass in grams of PbCl2 solid produced in solution mix. Now, just a footnote to keep things in perspective, don't forget what this is, here and here. Solution data, and that's, you should see moles on the end of that, even though it's not written there. That solution data, volume and molarity, will take you to what? Moles. And then you relate to the equation. Now, we have a metathesis between the sodium chloride and lead nitrate. So I'm going to put PbNO3, and that's an aqueous solution, plus sodium chloride, also aqueous. Give yourself a little room there. Sodium chloride. All right, so it'll become sodium nitrate. That will be aqueous. Be aqueous also. That's a mess. Plus your sodium chloride goes to this, plus the PbCl2 precipitant in here. Now, balancing the equation, we'll have to have a 2 nitrates, 2 right there, and we'll have to have a 2 right here. Sodium chloride and 2 in front of the sodium nitrate. So your reaction ratio is 1 to 2 in this expression. Okay, now remember how I set this up. I take these two and attach them to the reagents that are in the reaction. Like here's the sodium chloride, so I want to write it down in here, and the lead nitrate I want to write it over here. So I'm going to put me a little bar out here and write the lead nitrate first. So that's 22 milliliters, parentheses, 0.18 molar lead nitrate. And if the second one, you want to do it this way, just put plus 28 milliliters of 0.11 molar sodium chloride. Now all I've done here is write down the solution data attached to the equation. So this one is for lead nitrate, and the second one is for your sodium chloride, regardless of the coefficients right now. That's what was poured together in the beaker. When it's finished, we'll have 28 plus 22 milliliters when in the final volume. So I get 8, 9, 10. So that'd be 50 milliliters final volume. So you want to kind of keep that because you'll have to convert the moles that you get out of the calculation back to solution terms. Okay, so now I write this in terms that will take this to moles. That's molarity times volume. But that volume has to be in liters, 0.022 times 0.18, and parentheses mole PbNO32 plus 0.028 times 0.11, close that, mole of NaCl. Now multiply those together and find out the mole amounts put into the reaction. Sorry. Keep meeting up. Okay. Your excess is here, your limiting reagent. You have to make your calculation based on the limiting reagent. This is sodium chloride, look, right? This is lead chloride. So when you look at the equation, it takes 2 to 1. Same here, 2 to 1. So the moles of PbCl2 produced is equal to 1/2. That's what it says. See, that's half. 1 is half of 2. Okay, 1/2 of lead chloride moles. Oh, sorry. That should be 1/2 of the sodium chloride, which is 1/2 of the 0.00308, and that'll be moles of lead chloride yield used equals moles lead chloride produced.
What's the 1/2 come from? Okay.
Between these two, if I have 0.00308 mole of sodium chloride, it's going to be twice. I'm on this. If I use all of this, I'm only going to get half as much lead chloride. That's what the equation says. See, it balances at 2 here, so I got to use 2 of these. And this is based upon what we threw in the bucket. 2 to 1. 2 to 1. Study that. Right here. That's half of 2, isn't it? Is that half? Is that half of 2? 1. That lead chloride up there has a coefficient of what? 1. What's the coefficient on this one?
2.
We're going to use all of that.
Okay.
If I had 2 moles of chloride mixing with however much lead nitrate, I'm going to get 1 mole over here all day long. The ratios, or the reactive ratios, are the same. So if I have this many sodium chlorides, that's all I've got. I'm going to get half of that in lead chloride. Half as much. And that's what's so important that you see. And so many students miss that fundamental, that they can scale it up and down numerically by molar ratios. And working in any other terms is a nightmare compared to this. So the amount of the moles of lead chloride produced is 0.00154 moles. See, that number is the yield. We did 0.00154 mole produced here. And I used 0.00308 mole of the sodium chloride used. Well, this is half of that. That's why I split it in half. I'm looking at 24 people, and I assure you, you're not the only one that has to work with that. Go with it. The original problem is mass in grams of lead chloride produced. Well, we got it to moles. How do I convert moles to grams? Anybody?
Multiply by the formula weight.
Bingo, you're through with the problem. And so you work out the moles. Lead is 207. And that's 35, 77, 277. So that is 0.00154 times 277 grams of PbCl2 precipitant will come out of that reaction. I mean, it's real close to. And it's stoichiometrically perfect. 0.00154 times 277 is 0.43. That's good enough. 0.43 grams of lead chloride precipitate. How much lead nitrate would be left over? When you look at the equation up here, what's the relationship between lead nitrate and sodium chloride? 1 to 2. Balanced equation, coefficients. Yes? Everybody agree with that? Okay, this balanced equation, that's not a mystery. It is or it ain't. So, how much lead nitrate would I consume when I use 2 moles of sodium chloride? I'll ask it again. How many moles of lead nitrate will be consumed when I consume 2 moles of sodium chloride?
1.
Half. That's right, 1. Yeah, half as much. If I used 0.00308 moles of sodium chloride, how much of the lead nitrate was used? Half. That's right. So in this, if I want to know what the excess is, I'll divide that by 2. That's 00154. So I'll subtract out 0.0015. Sorry, guys. There is the excess lead nitrate. So you've got this many moles of lead nitrate floating around in solution. Well, this came out of solution. So this only thing you've got in that bucket is the lead nitrate and sodium nitrate. How much sodium nitrate? Well, it's the same as the sodium chloride. So if you used up 0.003808 mole sodium chloride in your reaction, how much of this do you produce? Well, since the coefficients are the same amount. So your sodium nitrate yield is 0.00308 mole. Once you get that, and you can play with it naturally in your mind, you'll be years ahead of the person sitting next to you in the next class. I've seen it happen too many times in the years. You can't imagine what this is how important this is when you get over to Chem 2 and start working with limiting reagents in systems like this. We'll give you one more and then we'll call it a day. Let me think. Let me think. I want to do this. Let me look up one because I want to get the ratios right on this one. Just down through. You take a break, Dave. Just get too much in it. I've been giving you all the little sample sideline issues that go with it. And I'm just going to flow through it. And you watch how I do this. Most of what you've been listening to today, and you can condense down to a very, mentally, a very few steps if you know where you're going. Now this is a neutralization of a weak acid plus sodium hydroxide going to sodium acetate plus water. It's a 1-to-1 reaction ratio right here.